So this is section 1.3, new functions from old functions. The purpose of this section is to discuss a little bit of transformations of parent functions as well as composition and operations with functions. So let's start off with transformations of functions. This should be a review from your summer assignment, but by applying certain transformations to the graph of a given function, we can obtain the graphs of certain related functions. This will give us the ability to sketch the graphs of many functions quickly by hand. It will enable us to write equations for those graphs. So let's first consider translations. Those are going to be our shifts left, right, up, and down. So if c is a positive number, then the graph of y equals f of x plus c is just the graph of y equals f of x, shifted upward a distance of c units, because each y coordinate is increased by the same number. Likewise, if g of x is equal to f of x minus c, where c is greater than 0, then the value of g at x at the same time as the value of f at x minus c, or c units to the left of x. Therefore, no, we're going to start that over. This is video 1.3, new functions from old functions. This video will serve as a review of transformations of functions as well as composition and operations with functions. So let's start with transformations of functions. By applying certain transformations to the graph of a given function, we can obtain the graphs of certain related functions. This will give us the ability to sketch the graphs of many functions quickly by hand. It will also enable us to write equations for the given graphs. So let's first consider translations. If c is a positive number, then the graph of y equals f of x plus c is just a graph of f of x shifted upwards that distance of c units, because each y coordinate is increased by the same number c. Likewise, if g of x is equal to f of x minus c, and c is inside the parentheses where c is greater than 0, then the value of g at x is the same as the value of f at x minus c, or c units to the left. Therefore, the graph of y equals f of x minus c is just a graph of y equals f of x that's shifted c units to the right. And so if I give you an example of the center function of this black graph is y equals f of x, this is our original function, or our parent function. By adding or subtracting c outside of the function will shift it up or down, and then adding or subtracting inside the function will shift it left or right. Now you should notice that when you subtract by c, you're going to be shifting to the right, and then when you add c, you're going to be shifting to the left, which is actually counterintuitive to what you think it's going to be. In general, and you're going to want to put this table into your notes, vertical and horizontal shifts, suppose c is greater than 0, so to obtain the graph of y equals f of x plus c, you shift the graph, the original graph, up c units. For f of x minus c, you're going to shift down c units. And then for f of x minus c, where the c is included inside the function, you're going to shift to the right c units. And if you're going to add c to the function where it's included in the function notation, you're going to shift that many units to the left. We can also, another transformation that we can do with functions is stretching and reflecting. So considering if c is greater than 1, then the graph of the function y equals c times f of x is a graph of y equals f of x stretched by a factor of c in the vertical direction, because each y coordinate is multiplied by the same number c. So for example, the graph of y equals negative f of x is the graph of y equals f of x reflected about the x-axis. So if my black graph here is y equals f of x, then y equals negative f of x, which is the yellow graph here, represents y equals negative f of x. And it's just the original graph, and it has been shifted or reflected across the x-axis. Similarly, if you notice, we can stretch and compress the graph. So if we multiply by fractions, we're going to be compressing the graph and making it flatter. So this is 1 over some value c. And if we multiply by numbers that are greater than 1, we're actually going to take the graph and we're going to stretch it vertically. So fractions will give me a horizontal compression, vertical compression, and then whole numbers being multiplied by the function will give me a vertical stretch. Also, you should notice that in the blue graph here, If I'm negating the x value inside the function, that's going to take everything and shift it over or reflect it over the y-axis. So you're going to want to put this in your notes. This is just a nice solid table for it. So suppose the value c is greater than 1. To obtain the graph of y equals c times f of x, you're going to stretch the original graph vertically by a factor of c. If it's 1 over c times f of x, you're going to shrink or compress the graph vertically by that factor of c. Multiplying by inside will stretch the graph horizontally. Dividing in the inside will compress horizontally. Sorry, I have that backwards. Multiplying on the inside by a function or a value will shrink the graph horizontally, and then dividing will stretch the graph horizontally. Multiplying by a negative value on the outside of the function will actually just reflect the graph over the x-axis, and multiplying or negating the x value inside the function will flip it about the y-axis, or reflect about the y-axis. So a nice demonstration of this is figure 3 illustrates these stretching transformations when applied to the cosine function with c equals 2. So the center function, or the pink function here, represents our original parent function, which is y equals cosine of x. And what they did in this first graph in figure 3 on the left is that they took y equals cosine x and they multiplied it by 2, which stretched it up so that the amplitude hits a maximum of 2 and negative 2. And so when you're multiplying by a number greater than 1, you're going to stretch vertically. And then they also took it and they multiplied it by 1 over 2. And what that did was compress the graph, or shrink the graph vertically. And then what they also did is they took the original function, which is y equals cosine x in the graph on the right, and they multiplied it by 2x, or they did the cosine of 2x, and that they shrunk the graph horizontally. And then they took the cosine of 1/2 x, and that actually stretched the graph out. So this still holds true. When you multiply by the whole function on the outside by a number greater than 1, you're going to stretch vertically. Numbers less than 1 but greater than 0 will give you vertical compressions. And then when you take that value and you put it inside the function, it's going to stretch or compress horizontally. For instance, in order to get the graph of y equals 2 cosine x, we multiply the y-coordinate of each point on the graph of the cosine x by 2. This means that the graph of cosine x gets stretched vertically by a factor of 2. So they're talking about this graph. So we take every y value and we multiply it by a factor of 2, and everything gets stretched vertically. So in your notes, you're going to graph y equals the square root of x, and we're going to transform it with these 4 transformations. So y equals x minus 2, or square root of x minus 2, the square root of x minus 2, where the 2 is included in the function, the negative square root of x, 2 times the square root of x, and y equals the negative square root of x, or the square root of negative x. So if you notice, the solution for this is that the graph of the square root function y equals x is shown. So here I have y equals the square root of x. This is my original function. The square root of x minus 2 has been shifted down 2 units. The square root of x minus 2, where 2 is included in the square root function, has shifted it right to the 2 units. This is the negative square root of x, where it has been reflected over the y-axis. 2 times the square root of x is a vertical shift, or a vertical stretch. And then when you pass the negative on the inside of the square root, which I know is kind of counterintuitive, it's been reflected over the y-axis. So in other parts of the figure, we sketch the graph by shifting downward. So this is just an explanation of what happened. Another transformation of some interest is taking the absolute value of a function. So if y equals the absolute value of x, then according to the definition of the absolute value, y equals f of x when f of x is greater than or equal to 0. And we get, and y equals negative f of x when f of x is less than 0. This tells us how the graph of y equals the absolute value of f of x from the graph of y equals f of x. The part of the graph that lies above the x-axis remains the same, and the part that lies below the x-axis is reflected about the x-axis. And we'll probably do a demonstration of that in class for a reteach. The other thing that we're going to do is we're going to combine functions. So two functions f and g can be combined to form new functions, f plus g, f minus g, f times g, f divided by g, in a manner similar to the way we add, subtract, multiply, and divide real numbers. The sum and difference of the functions are defined by f plus g of x is equal to f of x plus g of x. So, and f minus g of x is f of x minus g of x. If the domain of of f is A and the domain of B or G is B, then the domain of f plus G is the intersection of those two domains. So A intersect B because both f of x and g of x have to be defined. For example, if the domain, oh sorry, I got ahead of myself. If the domain of f of x is the square root of x, is A, and that's from 0 to positive infinity, and the domain of g of x is 2 minus x, where it's negative infinity to 2, then the domain of f plus g of x is going to be the intersection. So it's only going to be between 0 and 2. Similarly, the product and the quotient functions can be defined that fg of x is really just f of x times g of x, and f divided by g of x is f of x divided by g of x. The domain of fg is the intersection, but we can't divide by 0. Um, so the domain of f divided by g is the set x in A, that's the set x that's in the intersection of A and B, um, such that g of x does not equal 0. So it's any element that's in the intersection that doesn't make the bottom function be 0. For instance, so for example, if f of x is equal to x squared and g of x is equal to x minus 1, then the domain of the rational function f divided by g is x divided by x minus 1, is the set x such that x can equal 1. Or negative infinity to 1 union with the 1 to infinity. So it's basically anything that we can't, that doesn't make the bottom function not exist. Since both of the original functions, the domain was all real numbers, we can just exclude the 1. Generally, if we're going to write a domain, we're always going to write it in set builder notation if we have to exclude values. So this value is going to be, or this way to write the domain is going to be a little bit more desirable. There's another way to combine two functions to obtain a new function. For example, suppose I have y equals f of u, and that's the square root of u, and u equals g of x, which is x squared plus 1. Since y is a function of u, and u is in turn a function of x, it follows that y is ultimately a function of x. So we compute this by substitution. So if y equals f of u, and f is equal to g of x, which equals f equals x squared plus 1, and I know that that is going to be the square root of x plus 1. So this procedure is called composition because the new function is composed of the two given functions f and g. Basically what we're doing is if we're going to compose two functions together, we're going to take one function and pass it into the other, and order does matter. So in general, given any two functions f and g, we start with the number x in the domain of g and find its image, g of x, which means that we just take the function g of x. If this number g of x is in the domain of f, we can calculate the value of f of g of x. The result is a new function h of x, which is f of g of x obtained by the substitution of g into f. It's called the composition or the composite of f and g. It's denoted f composite g or f circle g. The reason why we have the circle is if we're composing multiple functions together, this will eliminate the necessity for multiple parentheses. So given two functions f and g, the composite function f circle g, also called the composition of f and g, is defined by f circle g of x is equal to f of g of x. Now the order matters, so whatever is always on the right is going to go inside the function. The order stays the same. So f circle g of x is f of g of x. If it was g circle f of x, it would be g of f of x. So order matters. The domain of f of g of x is the set of all x in the domain g such that g of x is in the domain of f. So in other words, if f circle g of x is defined whenever both g of x and f of g of x are defined. Figure 11 shows how f circle g of x in terms of machines. So we input g of x and we get g of x, or we input x into the function machine g and we get g of x, and we take that value and we input it into f of x, or f, and so we get f of g of x, and then this also does the same thing. It will give us to the same point. So let's try an example. If f of x equals x squared and g of x is equal to x minus 3, find the composite function f circle g of x and g circle f. So dealing with the first one, we're going to take the value of g of x, x minus 3, and we're going to pass it into f of x. So this is going to be f of g of x. So it'll look like f of g of x. Which means we're going to take this function and we're going to pass it into this function. So wherever I see an x squared, I'm going to write x minus 3 and squared. So we have f of g of x, or f circle g of x, which is f of g of x, which is f of x minus 3, which is x minus 3 squared, and we multiply it out. That would be x squared minus 6x minus 9, or plus 9. G of f of x will give me g of x squared will be x squared minus 3. So you should notice that order does matter, and they will yield two different functions. Remember, the notation f circle g means that the function g is applied first, and then f is applied second. In example 6, f circle g is the function that first subtracts 3 and then squares. In g of f is the function that first squares and then subtracts 3. It's possible to take the composition of 3 or more functions. For instance, the composite function f circle g circle h is found by first applying h, then g, and then f. So this is why we use circles, because this notation is much easier to read than this notation.